Okay, we have the beam, if it's rotating. We'll call it a track if we're rolling balls along the track. And here's domino, okay? Now, I can put this domino under the track. I can change the slope of the track by sliding the domino forward or backward. And I can roll the ball down the track with different slopes. Okay, so I put the domino back here. Let's say I've got this book here to counterweight. My track, this is a makeshift table. A couple of sawhorses, a speaker on its side, a couple of boxes, nice little board here, and then other stuff. Okay, just to get the thing up to the level where we can get it in front of the camera. Okay, so also notice I've got the domino, magnets here, and magnet is just a handy way to keep the steel balls corralled, keep them from rolling off the table. You can also use some sort of a tray, just make things a little more convenient. Okay, so if I roll the ball down the incline, it takes a certain time to get to the end. Okay, if I increase the slope, it'll get there more quickly. And notice I kind of hold down this end when I start, because if I want to get the slope I want to get a slope all the way up here, if I put the ball on it, thing's going to unbalance, so I'd have to do something like that. Okay. And of course I can set the domino lengthwise, get an even greater slope. Couple things that I noticed while playing around with it. Now I'm going to use two dominoes on their sides, and be careful about these dominoes if you're using them to measure distances and stuff. They have different thicknesses, so you want to be careful about that. Okay, so now if I release two balls at the same time, it's pretty interesting. Looks like this ball caught up with that one. It looks like, I don't know if there's a little, if they're magnetized, if they just geared together and came to rest. Now I've never even noticed that happening. So the fact that they've been on the magnet means that maybe we don't want to use that magnet to corral the balls, but maybe it does make a lot of difference. It'd be interesting to study that effect. Magnetize the balls, roll them down the ramp, magnetize one ball, not the other, see which ball goes faster. We can compare the speeds of the two balls. Now it looked like this ball got out ahead of the other one. Of course, maybe I didn't release them at the same time. Let's see what happens if I release this one slightly before this one. Yeah, got out ahead. Also, I noticed when I released this one, I gave it a little backward motion, not as much as you see here. We have to release them carefully so that we maybe have our finger on top and just pull the fingers off. Okay, they stayed pretty well together there, but I think one of them was still released a little bit late. Okay, so again, I'm going to do this. I'm going to release the first one a little earlier than the second. And we notice that they don't maintain a constant distance. How can we analyze that? That's an interesting question. And I'll probably have you investigate that at some point. Okay, other things we can do with the ramp. We can measure the slope of the ramp and time the ball going down the ramp to calculate its acceleration. If you have a lap timer, it's easy to do that. You do have to be careful about starting and stopping the lap timer at exact instants. So, for example, I want to start the thing when I release, so I click and try to time the next click so that it's simultaneous with the ball reaching the end of the ramp. If you got something down here that makes a little noise when it reaches the end, you can kind of listen to the noise and the click and see if they're simultaneous. So I can click, click. Now, don't know if you can actually hear whether the two events were simultaneous or not. The click and hitting the end of the ramp would have helped if I'd have. Okay, I just turned this thing 90 degrees so it makes more noise, so watch this. We'll click, click. I don't know if the click was before or after this thing hit down here, and our ears really can't detect which sound is first if it's much less than a few hundredths of a second, if the two sounds are much less than a few hundredths of a second apart. So there's an uncertainty in whether this click was simultaneous with the ball reaching the end of the ramp or a little early or a little late. That's an uncertainty you're never going to get rid of. With a little practice, maybe you can get good at it, and maybe you can figure out some kind of consistency measurement that would give you a better idea. Now later, we'll have ways to time this much more accurately. Okay, so if we put a domino on edge, and measure the width of a domino, I think we find that it's 2.5 centimeters, or maybe it's an inch. Yep. Let's assume 2.5 centimeters. If that's wrong, we can always adjust our calculations. Okay. Now, if the thing is 2.5 centimeters here, and from here to here is, let's say, 55 centimeters, then we can calculate the slope of the ramp. Assuming, of course, that our surface here is level. Okay, we can't assume the surface is level. Even if we have a good carpenter's level, we can't be sure of exact level. There's a way to compensate for that. Okay, so in any case, if my slope then is 2.5 centimeters out of 55 centimeters, and 55 centimeters would be the distance from the point where the domino contacts the ramp to the point where the ramp contacts the surface, along the surface, not along the hypotenuse. And maybe that doesn't make a lot of difference for small slopes. For big slopes it certainly does. In any case, we can release this from rest, time it, and determine from the results the acceleration of the ball on the ramp. And then we can maybe move this a little further down. So now we have the same rise, but the run is smaller, so the slope is greater, and we can easily calculate it. Being careful to counterbalance this end, we can release the ball. And of course, we want to be very careful if the distance we measure is the distance the ball actually travels. So if the ball is going to stop down here, the front of the ball hits the object at this end, and that's our final instant. So the distance the ball travels is from the front of the ball to that, in this case, that ramp, okay, whatever it is down here that we're using to stop it. Okay, well, we can do that, and we can get measurements that allow us to determine the acceleration on the ramp as a function of the slope of the ramp. Of course, we have the problem that our surface is almost certainly not completely level, and we can compensate for that by reversing everything. So we can do similar measurements. It doesn't always have to be with the same lengths, but it could be from here down to here. Okay, so we could measure acceleration versus slope in this direction. And if there's a difference in our acceleration versus slope graphs for one versus the other, then we can split the difference and get a really good result for acceleration versus the slope of the ramp. And the result's, of course, going to be limited by our ability to use the timer. Our ability, and another problem with that is that we're going to, everybody has a tendency, if they're trying to anticipate when the ball reaches this end, to either time a little bit early or a little bit late. That's going to induce some uncertainty in our results, and we have to be aware of those things and try to estimate their effect. So that's one thing we can do with ramps. Another is, let's just do this. We can make our famous V ramp. Got two balls. Now the balls you have might not be of the same diameter, and we have to know how to compensate for that. Easy enough, measure acceleration versus slope of the ramp for each ball. Okay, well, let's see what happens if we release these balls simultaneously. I wonder which, I think this one has a greater slope, so we probably have to, did a pretty good job there, okay, did a pretty good estimate. Okay, as far as I can see, okay, it looked like the collision was a little bit on this side that time, on this side of the V. When is the collision on the V? Might be good to use a lesser slope here. So this takes a little longer, and to use more distance over here to see what happens. Okay, this ball was past the V when they collided, so I should modify the position of this ball. Now, even further. Okay, that was bad. Okay, let's try this. What's going on? Yeah, okay. Ball should go on the other side. That was a bonehead thing. Okay. Okay, so maybe what we do is we look at the range, releasing this from the same point every time. We look at the range of positions from which we can release this that cause the collision to be on this side of the V, where we can see it, and then the range of positions here that would be on this side of the V. And in between we have a range of positions where we really can't tell which side it's on because it's happening too fast. So that's the kind of thing that we will want to look at and analyze. And of course, we assume we have uniform acceleration on these ramps, and that's pretty much the case. The ramps are pretty straight. Don't bend them. Don't play rough with them. You'll destroy them for this purposes of this experiment. Okay, so those are things we can do, and there are many other things we can do, but that's enough to get started.